Hello, welcome back to Chapter 7, Section 1, Exponential Functions, Growth, and Decay. We're doing problem number 6 on page 493, which is one of the guided practice problems. So in this problem, we're going to have exponential decay. A new softball is dropped onto a hard surface from 25 inches, which is about 2 feet and 1 inch, and it's going to rebound each time to about 2/5 of the height on each of the next bounces. So it's not going to come back as high as it was. It's going to be a fraction of each part, and that fraction is 2/5. So if I just think this out so I can understand what the problem is, I'm going to start and I'm going to drop the ball at 25 inches. On the first bounce, it's going to be 25 times 2/5. 25 divided by 5 is 5. 5 times 2 equals 10. So what that means is that it's going to start at 25 inches, it'll bounce and go up to 10 inches. On the second bounce, I take that 10 inches and I go 2/5 again. 10 divided by 5 is 2. 2 times 2 equals 4. So I can start by making kind of like a table. So my x value, and I'll make it horizontal this time, my x value is going to be which bounce that I have. The first bounce, the second bounce, the third bounce. And my y value is going to be how high it bounces to. So on my 0 bounce, which is when I drop it, I'm going to start at 25 inches. Then it's going to hit the ground, bounce back up, and it's going to bounce up to 10. On the second bounce, it's going to bounce up to 4 inches. And then on the third bounce, it's going to be 4 times 2 over 5, which is going to be 8 divided by 5, which is going to be about 1.6. Now, there's a couple things about this. First of all, we don't have negative x's. Why? Because x does not represent, well, okay, let me tell you what x does represent. That's a bad way of saying it. For all of the problems that we've done before, x was any real number, because we were just talking about graphs. Now this one actually represents a physics situation. The x's represent the bounces. What's a negative bounce? That doesn't make sense. So you're going to start at 0. We did a little bit of that with some previous problems where, like if we had not x but t, we were talking about time because we don't have negative time. So the problems that involved appreciation, depreciation, we don't have negative time. Okay, so that's why I started at 0. The other thing too is that, well, let me show you the graph. Okay, this one, when we do this in class, students get very, very frustrated with it. And I'm like, well, why? What's the problem? And then it dawns on me. This is not the height of the ball, because the ball is bouncing. The ball starts right here at 25 inches. This is my first bounce. I'm going 1, 2, 3, 4. Okay, and here's 5. These are bounces, and this is the weird part. You can't have part of a bounce. Like, what's half of a bounce? Okay, you got 1 bounce, 2 bounce, 3 bounce, 4 bounce. There's no fractions in between them. So they're not negative, they're not fractions. So this graph is actually wrong. But Desmos doesn't know that. So when I type this in the Desmos, it said, hey, here's your graph. But when I typed in my function, which I need to do, my function is going to be, and I'll say y because a of t doesn't make sense. How high is it at the beginning? 25. And it rebounds to about 2/5 of the height of each bounce. So I'm going to do 2 over 5 to x. All right? And this is where it's decay, but it's not depreciation, because depreciation involves money, okay, or the value of something. Okay, so we're not going to call this one depreciation. But yes, this is exponential decay. The only thing is that when I type this into Desmos, I get this function, because Desmos is okay with letting x be fractions. I'll move that up so you can see it. But we know that it's not really that way. So I only get these points. Like that. So dropping at 25, the ball comes down and bounces up to 10 inches. Then it comes down and bounces up to 4 inches. Then it comes down and bounces up to, what was it? I lost my place. 1.6 inches or whatever it is. Okay? And let's do this on my calculator so we can see what it looks like. Y 25 times 0.4. I'll do 0.4 to the x power. Make my table. And 25, 10, 4, 1.6, 0.64, 0.256. So now I'm down to like 1/4 of an inch. So after 5 bounces is down to 1/4 of an inch, which is right here. Okay. Now, this is where the model that we use for math doesn't really match up with the physics. And this is, it's called Zenon's paradox. And you will get way more into this when you get into calculus. But I love to have this conversation in class. It's like, if the ball keeps bouncing, and every time it bounces, it goes up a little bit more and bounces again, goes up a little more and bounces again, goes up, and it does that forever. But this is where physics goes, no, that's not going to happen, okay? Because we're not going to have an infinite number of bounces. Eventually, all of the kinetic energy of the ball is going to be depleted. And eventually the ball is going to stop. It's going to stop bouncing. So that's where the physics takes over from the math. The math is just a model of what's going to happen. But we have to understand physics to really get to what happens. Excuse me. So we can have these really good, deep, meaningful conversations. Does the mathematical modeling really describe exactly what's happening? And the thing is that there's other variables that are involved. Okay, there's entropy and a couple of other things I'm sure that we'll talk about later. Okay, so basically that's it. How many bounces would a new softball rebound less than 1 inch? So it looks like I said, where's my excuse me, looks like after 4 bounces I would get to like a little bit more than 1/2 of an inch. Hopefully you guys can see that. Okay, all right, good luck.